welcome back. Today we are going to be discussing one-sided limits and continuity from section 1.6 of the textbook. This first video is going to tackle computing and using one-sided limits. So we've talked about the notion of just a limit and haven't really talked about the whole sidedness issue. So this initial definition basically looks like the same definition from 1.5 for the limit as we approach some value. But there's a very subtle difference, and that is that when we talk about approaching a, we talk about approaching from a particular direction. So I don't anticipate you actually doing this, but if you looked back at the definition from before of just a limit as x approaches a of some function, it just has this part, as x approaches some value a, and doesn't have the underlying piece. So if we're just looking for values greater than a, somehow we have the possibility to get a different answer potentially than we would have looking from both sides simultaneously. So if we go from a value that's greater than a, and the function is actually approaching some number, we're calling that L again, I guess for limit, then again, we get something that looks very similar to our plain old limit definition from before. And I'll highlight the only difference right there. So everything else looks just like limit as x goes to a of f of x equals this limit L. What makes this different, the plus is supposed to indicate that positive numbers are found on the right side of the coordinate plane or the number line, and negative values are found from the left side. So if we start from the positive numbers and approach these values, whatever a is, then we're approaching from the positive side. If we start from the negative stuff and work toward whatever we come up with on our function, then we're approaching from the negative direction. So that's the other half of this. If x approaches some value and it does so from the negative side, so the left side, again just to illustrate values less than a, then the difference in definition is right down there. It's the negative little exponent. And it's not really an exponent, you're not really raising it to a power, it's just a notation that helps us recognize that this is a, quote, one-sided limit because we're only looking from the positive side, or we're only looking from the negative side of the real number line. So we'll try one of these out with a very exciting looking function. So this is our entire task here. We don't have a context, no word problems, no average cost yet. This is just trying to get a feel for what's going on with this function. So in words, we're trying to have x get closer to 1 from the right side, the positive side, and our job is to figure out what the output of this function is approaching at that point. And it turns out that we're going to basically do this from an informal process. There is a more thorough algebraic way we could jump into this, but I would have a hard time justifying why we would attempt that instead of a more informal process that will arrive at the same conclusion. So basically the informal claim is that if we come in from the right side, then this is going to look like some number on top. In fact, if we think about plugging in 1, we'd have 2 on top, some positive number. And then on bottom, plugging in 1 would be a problem because we'd have 1 minus 1 in the denominator. But if we thought about a number close to 1, 1.00, for instance, then our denominator looks like this instead. I sort of still don't care what the numerator looks like. There's some stuff up here. There's a squiggle. Perfect stuff. Then on bottom it looks like, I guess it would be 0.001. Dividing by a small number, though, makes this a very large number, the overall fraction very large, because we'd be dividing, in this little example, by 1,000. By 0.001, 1,000th, which is the same as multiplying by 1,000. So we have some positive number on top, a tiny positive number on bottom, which makes this equal to some large positive number. And that's the claim that this number just keeps getting bigger and bigger. So I just realized I've never actually, for you guys at least, have not written actual words down here. Now you can see why. So a claim is we conclude that this limit, the limit of this function, just approaching from the right side, is positive infinity. Okay, and maybe to help justify this a little bit more, since that justification is not terribly convincing, but if we add a visual element, this is the graph of that function, that x squared plus 1 over quantity x minus 1. If we look at it for values close to 1, can sort of see that as we approach from the right side, and this is kind of the visual that I want to employ here, as we approach from the right side, this graph starts to swoop upward, and there's nothing in its definition that's going to stop this from going up. So basically, as we approach from the right side, this could help reinforce the notion that the graph increases sharply upward and that perhaps this has a limit of positive infinity. Given that we've already introduced a limit definition, it seems like it would make sense to make the one and two-sided, although we didn't refer to it explicitly as a two-sided limit in section 1.5. But it would be nice to make these two definitions reconcile in some fashion, so we don't just have two related but slightly different things floating around with completely different definitions. So if it happens that we look from the right side of some x value, and then we also look from the the negative side, the left side of this x value, and we're looking at the same function. If they agree with one another, and by agree I mean that this limit is equal to that limit, and then we'll just pick some number L for them both to be equal to. So we'll say, look, if these two limits are the same, then we could actually define the limit that we had before as this L thing. So as long as approaching from the right side and approaching from the left side agree at that middle point, we can drop the plus and minus business and just write plain old A like we did before. And so this is that statement written again. So if the one-sided limits agree with one another, then we basically get exactly the same limit that we were discussing from the previous section. So let's try this with a piecewise defined function. If you recall from earlier in chapter 1, we're trying to review these a little bit from our college algebra experience, and this one's got a lot going on, and our task for this particular question is to compute the one-sided limits as x gets close to 1. And I think there's an argument that 1 is the most interesting point to look at because it's where this function changes definition. So for values less than or equal to 1, this top function is in charge. For values of x that are greater than 1, this bottom one's in charge. So something interesting could happen at the changing of hands here, sort of switching over from top to bottom definitions. Okay, so formally what we need to compute is the left-sided limit and the right-sided limit, or left-handed limit if you like. So this would be approaching from the left side, approaching from the right side. They will probably use different parts of this function. In particular, the function's defined for values x less than 1 by that top expression. So we're only going to be using that 1 minus x piece to describe the function when we have values of x less than 1. Let's take that one more time. Remember that piecewise defined functions have these domain issues where one portion of the function is only in charge for certain values of x. This is the function's definition if we pick values of x that are less than or equal to 1. Since we're approaching 1 from the left side, we're guaranteed to have these outputs be less than 1. So the limit as f of x, this whole big piecewise thing, is really just reduced to this one part of the definition. And then this equal sign is it represents great progress, because from the previous section, we would have had to do all kinds of breaking this limit as x goes to 1, of 1 minus the limit as x goes to 1, of x squared, etc. But we don't have to do that because from our prior section, we also had this theorem that says if what you're given is a polynomial, it looks like x to some power, then to some positive integer power, then you can simply take this input and plug it in for all of the x's and say, look, the limit is equal to what you get if you evaluate this expression at 1. So we get to use those properties, which is fantastic, even though we're looking at this, in theory, new thing, this left-sided limit. So we're going to plug in 1. That's what we get when we plug in 1. 1 minus 1 squared is 0. So we've successfully figured out this left-sided limit. Now we should turn our attention to the other side, the x greater than 1 part. So the function's defined differently. It's defined by this second expression when x is greater than 1. So the limit starts off looking the same. It looks like x goes to 1 of f of x, but because we're looking solely at the positive side, now recall that the one on top, excuse me, the one on bottom, the 3x plus 1, is the portion of this function that's in charge when we pick values that are strictly greater than 1. And since we're approaching 1 from the positive side, we're assuring ourselves that we will always have things that are 1 point something or other. They're definitely bigger than 1. And then we use that same rule of rational functions and limits. We get to plug 1 in. There's our input. Notice that the limit expression has gone away here because we actually evaluated this limit. We used that nice theorem to get to just this plugging in point. And then finally we've got 3 times 1 plus 1 for a grand total of 4. So we computed the left side and the right side. And nobody asked us this explicitly, but it's nice to notice that we computed this right-sided limit just a moment ago. We got 4. And we computed the left-sided limit a few minutes ago and got 0. And certainly I think you can agree that these numbers are not equal to one another. So what all that really means is that if somebody asked us about the limit as x going to 1 with no pluses or minuses, we would have to go back and say, look, let's figure out these two limits, figure out if they're equal, and since they're not, we say this limit does not exist. So it's not infinity, it's not 0, it's not, whatever. It's that we simply cannot say that it exists at all because the two sides of this function don't agree. That's it for our introduction to one-sided limits. We'll be back in the next and final video for this section with continuity.